Hello and welcome back. Let's talk about some trig integrals. Now obviously we know a lot of our trig integrals, such as the integral of cos x dx is sine x plus c, but let's talk about some more complicated ones, such as the integral of sine to the n of x times cos to the m of x dx. And all these n and m's mean is they could be 1, 2, 3, 4, 5, -1, -2, whatever. Usually positive counting numbers. And so what we're going to do with these is we're going to use our knowledge of the derivatives of sine and cos and our knowledge of u substitution. And so what we can do here is we can, let's say we had the integral of, say, sine squared x times cos cubed x dx. What we can do here is we can reduce this cos down to just a cos x by doing our Pythagorean identities. So we get this. Now we know the derivative of sine is cosine, so if we have just one cosine, we can use our sine as u and our cosine dx as our du. So what we'll get is the integral of u squared times 1 minus u squared du, where u equals sine x. Of course, du would equal cos x dx because we replaced it right here. And so what we're going to get here is 1/4, sorry, I'm reading the wrong one there, 1/3, sorry, sine cubed x minus 1/5 sine to the 5x plus c, I believe, yes. And so that's just evaluating this integral. We already know how to evaluate these. We would already know how to do a definite integral the same way by substituting our bounds of integration and everything. Now, that is easy to do if we have 1 or 2 odd powers on our sine or cos. Another example we would have is this exact same integral, but let's say we had the integral of sine squared x times cos squared x dx. Well, here we run into a bit of a problem because we can't reduce one of these down into a single sine and cos x, which would be the derivative of each other, keeping in mind that the derivative of cos is negative sine, of course, so we would put a negative in front of the integral. But what we can use here is our knowledge that sine of 2x equals 2 sine x cos x. And so what we can do is we can actually make this the integral of 1/4 integrals of sine squared of 2x dx. And this would be a good time to talk about integrals where we don't have a cos or we don't have a sine. We know that the sine squared of 2x, or sine squared of x, would be 1/2, 1 minus cos 2x. So what we can do here is we can replace this x with a 2x. That would mean that our 2x is now 4x instead. And so what this is just change this to an 8 by multiplying by 1/2. And this would become 1 minus cos 4x dx. That's a very simple integral. What we're going to get is 1 over 8 times the integral of 1 is just x, or the integral of dx you might want to think of it, minus sine of 4x times 1 over 4 using the reverse chain rule. That's an easy one. We know that if it was a derivative, we'd put a 4. If it's an integral, we put a 1 over 4. Don't forget our plus c. And so what we would get is 1 over 8x minus 1 over 32 sine of 4x plus c. Let me make sure I got that right. Yes. So that's our sine and cos integrals. Now let's talk about one other type of trig integral that we can have. And this is an interesting one, and we will come up with a very interesting result. Let's say we have the integral of tan to the n of x times secant to the m of x dx. Well, we know that the derivative of tan is tan x secant x, the derivative of tan is secant squared of x, and the derivative of secant is tan x secant x. So, we have another two different types of substitution we could use here. So let's hop into an example. Let's replace these with just a 1 on the tan and a 2 on the secant. So I'm going to evaluate this integral in two different ways. The first one, we're going to use u equals secant of x du equals secant x tan x. What we're going to get is we're going to get the integral of u, and then we have a secant x tan x left over. That's du, which is just 1 over 2, u squared plus c, which is just 1 over 2, secant squared x plus c. So that's the first one we get. Let's do it again. Let's use u equals tan x. And we can use this too because we have a secant squared of x. Du equals secant squared of x dx. So let's just go up here and rewrite it. We're going to get the integral of u du, again, which is 1 over 2 u squared plus c. But our u in this case is tan of x, so we get 1 over 2 tan squared x plus c. Now, we might think these are two very different results, but let's remember tan squared x plus 1 equals secant squared of x. So this just means that this constant is going to be the same as this constant plus 1/2, because of course we take out this 1/2. Let's set these equal to each other to see this. 1 over 2 tan squared x plus c. Let's divide by let's times by 2 on each side. So we'll get 2, we'll call this constant k, call this constant c, 2c. Tan squared x equals, or secant squared x equals 1 plus tan squared x. We can minus tan squared x for each side. Let's just take it out. So 2 times our k constant equals 1 plus 2 times our c constant. Very interesting. They're the same because our constants could be anything we want them to be. So that is basically all our trig integrals consist of. You could have some situations where you might have a fraction, where you might have a sine over cosine or things like that, where you have to change them into tans and secants or vice versa. But other than that, that is basically all of our trig integrals. And in the next video, we will use this knowledge to evaluate integrals where we might not think that trig is the answer. But you'll see it, and I hope you tune into that episode. Thanks for watching this one.